All right. Good morning, everyone. So let me first thank the organizer for the kind invitation. So yeah, today I'm going to talk about a computation of two-loop amplitudes contributing to top quark pair production in association with a jet at the Large Hadron Collider. And this is a work in collaboration with Simon Badger, Matteo Becchetti, Colomba Brancaccio, and Simone Zoya. So the top quark is a rather special particle in the standard model. So it is the heaviest fundamental particle, and it has the largest Yukawa coupling. And unlike the other quark constituent, the top quark decays before forming hadronic bound states. And through the top quark sector of the standard model, we can perform precision tests and investigate the presence of new physics. And this is particularly viable since the top quark is abundantly produced at the LHC, mainly through TT bar production. And it turns out that a large fraction of these TT bar events, they come with additional jet radiation. And here, understanding the TT bar jet final state not only is interesting in its own right, but also, due to the richness of 223 kinematics, but also important in improving our understanding of TT bar production process, both from theoretical and experimental perspectives. And there have been also measurements available from Atlas and CMS for this TT bar jet final state. And here on the right, I'm showing the TT bar jet invariant mass distribution as measured by Atlas collaboration. And here we see that the data, they have systematic deviation with respect to the current best theoretical prediction. So it's desirable to improve the accuracy of our theoretical predictions. And yeah, and the top quark mass is one of the fundamental parameters in the standard model. So here, the value of the top quark mass is important in the study of electroweak vacuum stability. And here, top quark mass extraction can be done using TT bar jet final states. Here in the when you extract the top quark mass using the so-called template fit method, you provide theoretical predictions that are sensitive for observables that are sensitive to the top quark mass, and you fit to the data, and you get the output for the top quark mass. And for these theory predictions, you need to provide the computations to the best possible accuracy. Now, increasing the accuracy of theoretical prediction in the framework of quantum field theory framework, in the framework of quantum field theory, perturbative quantum field theory, amounts to computing higher order corrections. So here, next to leading order QCD corrections is now 2 days standard, and it is desirable, however, to push to next leading order corrections, particularly in QCD, in order to keep up with the increasingly accurate LHC data set. For the TT bar jet final state, the theoretical predictions are available at next leading order accuracy, both including the QCD and electroweak corrections. And there are different variants of predictions depending on how you model the final state top quarks. For example, you can treat the top quark as a stable particle, or you can include the decay through either the narrowest approximations or using the full partial calculations. Now, in order to push the theoretical predictions beyond next to leading order, we need to do this NNLO QCD cross-section calculations. And yeah, there are these 3 ingredients of the computing NNLO QCD cross-sections. So here we have the double virtual corrections, which involve 2-loop amplitudes. And then we need the real virtual corrections, which involve 1-loop amplitude with extra parton radiation. And then we have 3-level amplitudes in the double real corrections that involves 2 extra parton radiations. Now, these 3 ingredients, they are separately infrared divergent. Now, in order to get the finite result, you have to employ some kind of subtraction schemes. And here, I list some of the NNLO subtraction schemes that have been applied to 2-to-3 scattering process. For the 3-level and 1-loop amplitudes, they are pretty much automatized these days. So the remaining bottlenecks in deriving this NNLO QCD predictions for these TT bar jet predictions is in the computation of 2-5-1 amplitudes. So the main challenge lies in the evaluation of Feynman integrals and the determination of the corresponding rational coefficients, which are highly non-trivial for multi-scale process, i.e. process with many masses or many external legs. Yeah, here I'm just quickly flash the state-of-the-art of two-loop 5-point amplitude calculations, mainly including QCD corrections. So for the case of fully massless and one external mass case, the full set of Feynman integrals have been computed, and the solutions are written in terms of a basis of special functions called pentagon functions. And here the efficient numerical implementation has also been available. Now, for cases with more masses, either internally or externally, there have been some works in the past few years, mainly including the planar contributions. Now, thanks to these Feynman integral computations, this allows for a number of amplitudes to be computed. So particularly for the fully massless and one external mass case, and in particular for this fully massless case, all the processes that we are interested to study, they are available analytically in full color. However, for the one external mass case, mostly they are available in the leading color approximation. So only recently this fixed BB bar final states is available in full color, and this W plus 2 photon case available, however, only numerically. But however, thanks to these two-loop amplitude computations, a number of NNLO QCD cross-sections have been able to be derived for different processes. So here, yeah, I'm just showcasing some of the phenomenological results that have been computed. And yeah, I mean, if you can see here, mainly the main conclusion is that the NNLO QCD corrections are important in two ways. First, to improve the agreement with the data, and second, to reduce the theoretical uncertainties. All right, so yeah, back to the two-loop amplitude computation for TT budget production. So here, in comparison to the fully massless and one mass external case, for this TT budget process, we see increase in complexities due to the presence of masses internally and externally. So in particular, in the computation of Feynman integrals, due to the presence of internal massive propagators, we encounter functions beyond polylogarithms. And yeah, in the determination of rational coefficients, we have to deal with high degree rational functions. And also we have to deal with the presence of massive spinors, which in general introduce more difficulties in the computations. There are two scattering processes contributing to this TT budget production, the TT bar plus 3 gluon and TT bar plus QQ bar gluon processes. And here, yeah, we focus only on this for the moment in this TT bar plus 3 gluon scattering. And here we work in the leading color approximation, where we include only the planar Feynman diagrams. And here we take leading contributions on the number of color, as well as the number of closed Fermion loops contributing to the Feynman diagrams. All right, so the computation of two master integrals for TT budget productions in the leading color approximations have been studied in these two papers. So here there are three Feynman integral families that need to be computed. So the first, these two integral families, the so-called pentabox A and pentabox C, their differential equations can be derived to satisfy the to have the canonical form, such that the solution can be written in terms of iterated integrals. However, the one remaining family, the pentabox B, so this family involves elliptic sectors, and also there's a nested square roots present. So in their work, instead of writing the differential equations in a canonical form, they write the differential equation this way, where this power of epsilon runs from 0 to 2. However, they try to write these connection matrices as close as possible to the canonical form, such that the polylogarithmic sectors lives in this term, and then the remaining terms that proportional to the one forms are the ones that involve these elliptics and nested square roots. For the master integrals in the elliptic sector, they are chosen to start at epsilon to the fourth. And yeah, very recently, the canonical form of differential equation is recently available by this group of people. Now, In their paper, they obtain numerical solutions using generalized power statistics method. And yeah, there are a number of public implementation of this method available in the market. Now, so in our recent work, we want to go further. We want to write the master integrals in a basis in terms of special function basis. You might ask why we want to do this, because in principle we have only we have already numerical evaluation of the master integrals that allows for computation of amplitude numerically. Well, in view of the analytic computation of the amplitudes, writing the integrals in terms of special function basis allows us to have analytic cancellations of the ultraviolet and infrared poles, and this allows us to derive the analytic form of the finite remainders, which in general is the simplest form of your amplitudes. And also this will lead to more efficient numerical evaluation for phenomenological application. Now, to construct the special function basis, we use the so-called pentagon function approach. Here, I just briefly discuss how the construction goes. So the input is the canonical differential equations and also high precision boundary values of the master integrals at a boundary point. In this case, we take from this ion flow package. And here we take the epsilon expansion of the master integrals as our special functions. And here we take only up to epsilon to the fourth. This is the order we need for NNLO QCD computations. And here we start from canonical differential equations and write the master integrals in terms of chain iterated integrals. And then at symbol level, we extract independent master integral components using Gaussian elimination and shuffle relations. And then here at this point, since we have relations among master integral components, we need to specify our preferred ordering. So for example, we prefer lower weight functions over the higher weight ones, and we prefer one loop functions over two loop ones. So here at this step, after this step, we have extracted algebraically independent and irreducible special functions. And finally, yeah, we write this ansatz that the master integral components are polynomials in the this f in the special functions and the transcendental constants. And here, yeah, the coefficients alpha, beta, and gamma here is fixed. They are fixed either from symbol level analysis or by evaluation at the boundary point plus rationalizations. Now here we have constructed this special function basis for canonical case. Now, what happened when we don't have a non-canonical form of differential equations? So here, this is the differential equation for the master integral components for this pentabox B that I've shown you earlier. So here we have three connection matrices due to these three epsilon orders that appear in the differential equations. So here, yeah, basically we use the information from boundary values to determine which terms vanishes. So for example, we work order by order in epsilon. So at W equals to 0, so the 0th order in epsilon, the right-hand side of this differential equation vanish. So here, all the at weight 0, all the master integrals are constant. And then at weight 1, so these two terms, they vanish. So here, we end up with canonical form of differential equations, which can be solved in terms of iterated integrals. Moving on to the epsilon squared term. So here, we have terms that are proportional also to the one forms. However, when we evaluate the these coefficients at the boundary points, they turn out to vanish. So in the end, so this term, for example, for these 15th master integrals, so here we end up with canonical differential equations, which can be solved in terms of iterated integrals. And the same goes for epsilon cube. And for the epsilon to the fourth term, yeah, we simply take the master integral component as our special function basis. And this is, for example, what it looks like for this, for example, for this this master integral 15 in the pentabox B families. So here, yeah, in this pentabox B family, there are 6 master integrals where the epsilon to the fourth components are not written in terms of iterated integrals. And yeah, so putting everything together, so here, so we consider the special functions contributing to this partial amplitude. So this is partial amplitudes where the 3 gluons are ordered in the 3, 4, 5 ordering. So there are 237 special functions. Here, 12 of them are non-polylogarithmic. And in order to numerically evaluate these special functions, we use differential equation method where we construct differential equations for these special functions, and we solve them using generalized power series expansion method. So in particular, we use these two package, so diffx, which is mathematical implementation, and this line, which is a C implementation that's recently available. So here we study the performance of the numerical evaluations using this generalized power series expansion method. In particular, we study the so-called evaluation time per segment. So when solving the differential equation using this generalized power series expansion method, the path from your boundary point to the target point are divided into several segments. So here, yeah, we simply study the average evaluation time per segment. And in these studies, we collect about 1,000 segments from a random sample of points in the physical region. So here, yeah, on the left is the average evaluation time per segment for all functions. So the average evaluation time is about 300 seconds. However, if you just isolate the differential equations that contributes to the non-polylogarithmic special functions, the average evaluation time is about 16 seconds per per segment. So here, okay, you might worry that, okay, now my polylogarithmic functions take a long time compared to the non-polylogarithmic special functions. However, there's already implementations, numerical implementations for these polylogarithmic special functions that have been implemented for fully massless and one mass case. So here, yeah, we can simply do the same thing and have much faster numerical evaluation. All right, so now that we have constructed the basis of special function for our tight-bar jet amplitude computation, we can use it for our amplitude computation. So here, we work with helicity amplitudes, where our strategy is actually to fix the helicity of the gluons, but to expand the massive spinor in form factors in this form. So here, these helicity form factors can be obtained from the so-called contracted helicity amplitudes, and these are the 4 massive spinor structures you can have in the for this tight-bar plus 3 gluon process. Now, having the amplitude written in this way, it is straightforward to square the amplitudes or to attach the decay amplitudes. Or if you want to map to different massive spinor representations, this is also easy to do this from these representations. In our calculations, we construct these contracted helicity amplitudes using 4-dimensional projection method. So we perform the analytic computation of the leading color tight-bar plus 3 gluon amplitudes at 2 loops using a finite field framework that takes Feynman diagram as an input. So essentially, the idea in this framework is that all the algebraic operations you need to perform in your amplitude computations, they are replaced by numerical evaluation over finite fields. And here, I mean, performing the calculation this way allows us to bypass large intermediate expressions and only target the simplest form of the amplitude, which in this case is the finite remainder of the amplitude. So this is the representation of the amplitude after you subtract ultraviolet and infrared poles and you perform epsilon expansion. So here, yeah, so basically we implement an algorithm to compute this coefficient of special function monomials in the finite remainders numerically over finite field, and we extract the analytic expressions from multiple numerical evaluations. I mean, this way, sometimes, in most cases, the analytic expression is still too complicated. So we have implemented different layer of optimizations to drop the complexity of the analytic reconstruction. So for example, we guess denominators using letters of the alphabet. We search linear relations among these rational coefficients in such a way that we can write the complicated coefficients in terms of the easier ones. And in the end, we only need to reconstruct the easier ones. And yeah, we implement the on-the-fly univariate partial fraction decompositions within this finite field reconstruction. And one of the crucial ingredients in our framework here is the use of optimized IBP relations that we obtain from NIT IBP package by Yang Zhang and collaborators. So here, we basically we generate relations between from NIT IBPs, and we solve numerically over finite fields using Laporte algorithm. Once we solve this numerically, we chain the numerical solutions to the next step of the calculation. So here, in our approach, we do not derive analytic form of the IBP table. And yeah, I mean, using these optimized IBP relations, in fact, gives us substantial improvement on evaluation time and the memory usage, such that the IBP reduction is no longer a bottleneck in our computation. Since we work with finite field, we need to use rational parameterization of external kinematics. And yeah, in this case, this is achieved using momentum twister parameterizations. All right, so we have successfully reconstruct the analytic expression of the TT bar plus T gluon amplitudes in the leading color approximation at 2 loops. And here I'm showing the summary of analytic reconstruction data. So the numbers that I'm showing here are the maximum polynomial degrees in the numerator and denominators. And here, different columns shows different optimizations that we implement in the different stage of the computation. So for example, the first one is what we get if we compute mass normalized amplitudes in the master integral representations. Now, once you go to the special function basis and subtracting the finite remainders, you see quite a big drop in the maximum degrees. And then here we search for linear relations and then guess the denominators. And then this part, we perform univariate partial fraction decompositions. And this is where the huge drop in degrees appear. And in the end, yeah, this is the final number of points we need to evaluate in order to fully reconstruct the amplitude analytically. So here in the computation, we consider these 3 independent helicity amplitudes, helicity configurations. And yeah, here we run simply these 3 helicity configurations simultaneously. Now that we have the analytic expression for the finite remainders, we can use them to build the hard functions. So here, yeah, I'm presenting a preliminary result for the numerical evaluation of the hard functions. And this is really the numbers that go into the cross-section calculations. Yeah, this is, for example, the result for this benchmark phase space point in the physical region. Yeah, actually, yeah, this brings me to my summary. So yeah, we're addressing the main bottleneck in deriving TT budget production, theoretical prediction for TT budget production at NNL QCD, which is the computation of 2 loop 5-point amplitudes. So I've described the construction of special function basis in the case of non-canonical differential equations. So we managed to derive analytic expressions for the TT bar plus 3 gluons helicity amplitudes at 2 loops in the leading color approximations, which we employed functional reconstruction techniques using finite fields. And yeah, we're able now to perform numerical evaluations of the hard functions that will enter the NNL or QCD cross-section computations. Right now, yeah, we are still working on numerical evaluation of the special functions that can handle a large set of phase space points that is needed for the cross-section computations. In particular, we try to have these numerical evaluations to run on a large-scale cluster, and we want to have robust control over numerical accuracy. Yeah, and then we still need to work on the analytic computation of this TT bar plus QQ bar gluon scattering process. However, we believe that this should have should be easier compared to this TT bar plus 3 gluon amplitudes. And once all the two-loop amplitudes are available, hopefully we can derive the NNL OPHD cross sections for this T-bar jet production and use them in phenomenological application not too far in the future. And yeah, thank you very much for your attention.